I got into lockpicking during COVID because this right here is the best fidget toy ever made. What is it, you may ask? Well, it is a practice lockpicking lock where you can take out all of the individual pins and springs and replace them with any other one that you want. Basically, when you're learning how to try to lockpick a lock for the first time, you can create a lock as hard or as easy as you want, and so customize it to be exactly at your level of skill. And that's really cool and obviously fun to fidget with. But it got me thinking, can I make a robot that does the same thing? And that is where this guy comes in. That's right, the most customizable lock ever. It doesn't look like this. It looks a lot more like this. Sure, in this one, you can take it apart and swap out all the pins, which is kind of a pain in the butt, and you have to sit there fiddling with an Allen wrench for 20 minutes. But in this one, you can swap out the pins anytime you want through software. You can make a game out of it, etc., foreshadowing for the rest of the video. But even more importantly than that, because of the way that we designed it, you can physically have any pin imaginable. And in this one, if you want to swap out the pins, you have to actually buy the pin. It has to be manufactured, made out of a real piece of metal. Whereas in this one, it can be anything you can possibly imagine, including things that are actually physically impossible to design for one of these real locks. We'll get to how this guy works very soon, but first, let's go over the basics. How does a lock actually work? The way that a lock, locks, is that it has a cylinder inside of another cylinder with some holes drilled inside. So the inside cylinder is the part that spins and will actuate like your deadbolt or whatever, and the outside cylinder is going to be bolted to your door and won't move. In those holes that are drilled out are some of these pins, which have different heights, such that you need them to be all at this exact height of this little line, the line between the two cylinders, which is also called the shear line. Otherwise, they physically get in the way of the inside cylinder being able to turn. A key is just a piece of metal that's cut into a shape that perfectly lifts each of the pins to the exact height that they need to be at the shear line, and obviously it also gives you a little bit of leverage to actually be able to turn that inside cylinder. Sounds like a perfect system, right? So how do lockpickers get past it? Well, if locks were perfectly machined, if we were able to fabricate things exactly as they were intended to be in complete ideal conditions, then they might not be able to, or at least it would be a lot harder. But lockpickers are able to take advantage of the fact that, unfortunately, we live in the real world where manufacturing processes have defects, they have tolerances, and you're able to use these defects to be able to break into the locks. To show you, I've made this little 3D printed demonstration. This is a cross-section from the front of the lock, so looking at it as if you slice it open this way. This right here is the inside cylinder, which is what we want to turn inside of this big outside stationary one. And this is what we call the pin stack. Normally there'd be a spring up here too, which is important to know for when we get further down the robot, but in this case I'm going to forego it for the demonstration. This part of the pin is called the key pin, and the flat pin on top, which would normally be a cylinder obviously, is called the driver pin. Both of these pins can be different heights, which is why you have different keys for different locks, but for this demo I'm just going to demo with some different height driver pins. You can see that in order to be able to turn the inside cylinder, I have to lift the key pin to exactly the right height, right? Well, watch what happens when I apply a constant turning force, or torque, with this tension wrench to the inside cylinder. Now, when I lift the pins, they're both scraping against the side of the cylinders, and as soon as I get to the shear line, the driver pin pops up above the cylinder and the key pin gets stuck on the shear line, keeping it the exact height that we need it. And you can see that the only reason why this works is because I printed it with this manufacturing tolerance, making it so that there's a little bit of slack when you apply tension to the inside cylinder, and therefore, right above the shear line, there's this little overhang in the two cylinders. Obviously, this is exaggerated in scale from the real tolerances that you have on a real lock, which makes it easier to see for the demonstration, but in principle, it's exactly what happens in a real lock as well. We'll come back to that demo to cover some more advanced topics later in the video, but for now, let's actually make some progress on this guy, huh? My idea was this. In lockpicking, there's basically two main experiences. There's the experience of moving the pin up and down and feeling the tension against the side of the cylinder, like we just talked about in the demo, and then the other part is applying that tension to the inside cylinder. I would say the one that is kind of more iconic for lockpicking is the action of moving the pin up and down. So let's start with that, shall we? So the more friction there is of the pin against the side of the cylinder, the harder it is to move, right? So as you're getting up closer and closer to the shear line, the tension increases and increases until finally you get to the shear line and pop! The driver pin comes up, you hit that shear line, you kind of hit that wall, and suddenly there's basically no friction at all. That instantaneous change in friction ends up feeling like a click or a snap. So now this is when I'm going to take you back to the glory days of 7th grade. We're going to have to turn this word problem into a mathematical function. The idea is that we want to be able to describe the level of difficulty you have in moving the pin up and down versus the physical location, like how vertical up and down the pin is inside of the pinway. That way, when we're making the robot, we can have a motor that applies a different level of friction depending on where the software determines your current pin location to be. Every bone in my body that has learned anything in math and science classes is telling me that as the independent variable, the x-axis should be position, but ooga booga, the pin go up and down, so it go on y-axis. So yeah, in English, what I mean is that because the pin is moving up and down, I thought it would be easier to visualize it as the position on the y-axis. On the x-axis, going horizontally, we're going to have the level of friction that we're applying in that current moment. So you can see that if we're trying to map out the standard pin example, when we move the pin up, the chart goes right as the friction gets more and more and more and builds up, and finally we pass the shear line and immediately drops back to basically 0. This chart is the mathematical description of what a click feels like. So now, in order to make this guy, we just have to go in the opposite direction. We have to be able to take one of these mathematical charts and somehow create it via a motor. My first inclination was that we should do something very similar to my previous video, where I made a fishing rod that has different difficulties of fighting against the fish, and the way that that worked was by using a small DC motor and applying similar principles as how you get regenerative braking in cars to make it more or less difficult to turn the generator. In that video, we only had 4 different discrete levels of difficulty, and then we were kind of swapping between each of those 4 difficulty levels. After posting that video, I thought of a bunch of different engineering solutions for how we can, instead of having 4 discrete buckets of difficulty, we could have a whole sliding curve and have basically any difficulty we wanted from a minimum to a maximum. And the best one that I came up with was to use this what to me is a fairly complicated op-amp circuit as somebody that's not an electrical engineer. And the way that works is, based on how much voltage you're applying here at the input, it changes how much current you're allowed to draw over here at the load. So the way that I thought this could work is that the more current you're allowed to draw from the DC generator, the harder it's going to be to turn, because the more current that you're able to draw from the generator, the more work you have to put into spinning it, because that energy has to come from the rotational force of you moving the motor. You might be thinking, wow, you're glossing over this a lot for the perfect solution, right? That must mean that it didn't work, and that we're going to have to move on to something completely different. And, well, sort of. Actually, it worked really perfectly, and if I was going to remake the fishing rod from the last video, I would 110% use this. It was a perfect solution to that problem. Unfortunately, this is a very different project, and it has some slightly different project requirements, and I am a perfectionist, and it just wasn't good enough for me. The issue being that moving the pin of the lock has a lot more what I would describe as dynamic range requirement. Basically, when the pin is easy and it's free in the pinway, it should feel almost effortless. It should just glide without providing any resistance back to you. But when you're really close to that click, it should actually feel really difficult to move up and down. That difference from going from really, really difficult to immediately extremely easy is how you get a very satisfying click. It's how you get that snapping feeling that we were talking about earlier. And without it, you either get an extremely wimpy snap where it never felt very difficult, and so you don't get that kind of release of tension, or B, the lock feels super crunchy and hard to move even when it's supposed to be very free in the keyway. I tried so many motors. Literally, at one point, I went through every single motor I had with one of the design solutions, and for every single motor, I had to print a custom motor mount or some other custom testing methodology to see if it will work, and eventually I caved and bought a bunch of other motors, and none of those motors worked, and I dug out my brushless DC motors thinking that because they have 3 phases that I could somehow have a combination of 2 phases or all the phases, and maybe that would help. Anyway, nothing worked, and I realized that I just have to move on one day when I was brushing my teeth and looked in the mirror, and I don't think this is a coincidence. I've genuinely found this giant gray hair right at the top of my head.
This is what the motors did to me.
So I did what every engineer does best when they don't know how to solve a problem. I procrastinated by solving a completely different problem. Remember that the whole point of this is that right now we're doing the pin section, but we have a second completely different section, which is the tension that we're applying on the keyway. Like I said in the demo, when you're actually lockpicking, you have to constantly apply this force or this torque on the inside of the cylinder. Otherwise, you won't get that binding action near the shear line. And without that, no simulation of a lockpicking experience would actually be even close to complete. So let's work on that, shall we? I thought this would actually be a much more approachable problem. And the reason why is because you don't really need any of that dynamic range that we had before. In fact, you actually basically want no dynamic range. What you want is when you can't turn the lock, you should absolutely not be able to turn the lock. It should completely break you in place. And when you can turn the lock, well, it should be as easy and effortless as when you're turning the lock with a proper key, right? So the solution felt pretty obvious. All we have to do is be able to determine whether you're in the free section or if you're butting up against the wall of the lock. And if you are butting up against the wall of the lock, then we have a motor that stops you in your tracks and doesn't let you turn any further. There's one particular type of electric motor that's really good for situations like this. You might have heard of it. It's called a stepper motor. They're commonly used in things like 3D printers. The thing that makes a stepper motor different from other electromagnetic motors is that the positioning of the electromagnets makes it so that when you're moving the motor, it's almost like clicking gear teeth, and that gives you 1, really precise movement, and 2, more importantly for us, when the motor is at a standstill, you can apply a lot of braking pressure. Basically, you're like locking the gear teeth in place, and so the more current that you apply to the motor, the more braking force that you have. So what we can do is just measure where we're at in the keyway, and if we're supposed to be able to move, then we apply no braking torque. And if we want to stop the motor, then we just apply the maximum amount of current that we can to the motor, and it stops dead in its tracks. You can see in this little demo that this actually works extremely well. And with this giant stepper motor, which is like the biggest stepper motor that I own, I legitimately can't turn it at all. You can see that my torque wrench is actually flexing because of how hard I'm pushing against the braking force of the motor. I have to admit, it felt really nice to just have a win under my belt, even if I knew this part was going to be easier. But then an idea hit me. That instantaneous difference between being able to freely move and immediately not being able to move at all, well, I would call that like perfect dynamic range, right? And so a thought struck me. If we could just apply this exact same principle of this like stepper motor braking to our first problem of trying to make the pin movement up and down more difficult on a curve, well, surely we could get perfect dynamic range in that pursuit too, right? And the issue is that with one of these cheap little stepper motor drivers, you can't. But I found these specialty stepper motor drivers that are used for like fancy 3D printing solutions, and that actually has the exact thing that we need. Basically, it's got a little microprocessor on it, and by communicating with it, you can send it a command to make the maximum braking torque more or less. And these things have a lot of resolution on them, and you can send commands and something crazy like tens of thousands of commands a second. The only other bit we need to know is where we are in the vertical position of the pin, so we can tell, where we are on the y-axis. We can do that with this magnetic encoder. I'm not going to go super in the weeds on how one of these works, but very simply, most magnets that you find are going to have the North Pole on this side and the South Pole on this side, but there's these special magnets that you can buy where the North Pole is this side and the South Pole is this side, and there's a line down the middle this way, and this little microchip can tell the rotation of this line down to a fraction of a degree of rotation. That lets us know exactly where our motor is, and because of this rack and pinion mechanism, which transforms the rotation into linear motion, doing just a little bit of math lets us translate the angle of the motor into the vertical position, that y-axis figure that we're looking for. I made this tower-looking thing that holds the big torque wrench motor on the bottom and a linear pin motor on top, and then most importantly, it perfectly positions the encoder board so that the magnets are exactly where they need to be for it to be able to read. One of the annoying things with these encoders is that you have literally a fraction of a millimeter of wiggle room in this regard. I also made this guy, which lets you move the tension section with a standard sized lockpicking tension wrench, and this thing, which connects to the rack and pinion mechanism, which has a slot to let you move the rack mechanism with anything that's got a hook on it. And most importantly, I made this box. It's got a big, goofy cartoon, Kingdom Hearts-esque lock on the front so that you know that it's a lockpicking minigame. Just kidding. The real important bit is that it's got two mounting points for springs, one on top, which mimics the springs that are here against the actual pins, which is a real spring that exists in locks. And the other spring is here on the back, and it pulls against... Put that back here. And that one pulls against the tension wrench going in this direction. Otherwise, you'd just be able to let the tension wrench go, and instead of snapping back like that, it would just hold in one place and there would be no tension at all, basically. So I've got it set up so that it reads your position and then translates that into a difficulty and sends that to the stepper motor. And it's going to track our click curve that we have over here, and oh man, it really clicks. It feels perfect. I took a few different tries, and I had to use every stepper motor I owned again, but with the absolute smallest stepper motor that I had, when the braking current is at a minimum, it basically felt like no resistance at all. It was just super easy to move up and down. And at maximum, it's basically completely impossible to move. So adjusting the range gives us hundreds of different values in between that we can adjust to, from super easy to super hard. And now that we have that out of the way, now we can get to the real point, which if you've seen any of my previous videos, is that we have to make this into a game, obviously. That's right. It would be cool to have a lockpicking simulator, but it's even more cool to have a lockpicking minigame, like in Skyrim or something like that. What I thought to gamify the system is to basically use the position of the tension wrench from left to right as sort of like a progress bar. So you would start here and you would know how far your progress in the game is the further to the right that you get, and then you know that you win when you're maxed out all the way at the wall. The trick here is that in a normal lock, obviously you wouldn't have one pin, you would have 6 of them, and you wouldn't be able to actually turn the lock. You wouldn't quote unquote win until you got all 6 of them. And so you'd have to progress by getting each of the individual pins correctly. In this case, you only have 1 pin, so it'd be really anticlimactic if you just got it up to the shear line and immediately let you win. My first thought was maybe you would have to move the pin position up to the shear line and then leave it there for a few seconds. That also feels a little bit anticlimactic and kind of boring and also easy to game the system on. So I came up with a better system, which is what if you had to wager your progress in the game by moving the tension in the opposite direction of where you want it to, and this way the tension is going to be free, right? Because the wall is only in this direction. And when you move it back, it lets you make a guess as to where the shear line is. If you're correct, then you can snap the tension wrench further over to the right and make more progress towards winning the game. But if you're wrong, then the software stops you, and now you've lost progress because you've gone in the wrong direction. I thought it was a kind of clever way of gamifying the system. I wrote some code to basically turn the system into a real game. You can see the position the pin is currently at with this blue line, and I marked basically the area that I would consider close enough to the shear line to win in the game with this green box. It looks like it's really lenient on camera, but that's because the camera is like very zoomed in. In reality, this is actually like a very small physical zone of being correct. Let's try it out.
By the way, if it wasn't obvious, I can actually see the stuff on the right side of the screen while I'm doing the lockpicking minigame. That's just for your benefit as a viewer so you can see what's going on.
You can see I'm making some good progress here. Got that one correct. Okay. And okay, I've won. And this is fun enough with just standard pins, but remember how I said we were going to go back to the demo to explore some more advanced topics? Well, let's revisit it, shall we? It turns out that in order to combat lockpicking, they made more exotic and harder to pick pin types. There's lots of other different types of pins, but they can basically be split into 3 categories. There's ones that look like the standard pin, and then the second category is ones that look like this, which are called serrated pins, and they're designed such that each of these little ridges is going to make smaller little clicking feelings when they pass. And that confuses you with the like real big click of the pin actually passing the shear line. This is pretty simple to simulate. You can see that we just add a bunch more of the same click shape, but with slightly smaller peaks near the shear line, but not quite at it. And the third major category, which I also think is by far the hardest pin type for me to personally pick, is called the spool. This one not only changes the way that the pin feels, but each of these lips here actually gets caught on the shear line in either direction that you're going. Meaning in real life, if you get stuck in the spool zone, then you actually have to release tension on the wrench so that you can basically reset the position in the keyway and slide the pin back into its original position and try again. These are not only difficult to figure out how to pick with one of these practice locks, but it also means that we're actually going to have to add a whole new feature to our software simulation on this guy. Now we have this special condition where if we're simulating a spool, if we get stuck in the super duper hard area here, which feels almost impossible to move with a pick, the software is actually going to check if you're moving the tension wrench to the left, just like it would if you're making a guess. But this time, instead of making a guess, it's going to change the curve up above. And once you put full tension back on the tension wrench, it changes it again so that now you get another try, but you can get stuck in the spool zone again up top. Hopefully you can see that these are just a few different examples of ways that you can make software versions of like these real pins that exist in real locks. Even though there's like a bunch of different subtypes of pins, most of them are really just a variation on the theme of one of these 3 different groups. In reality, I've pretty much showcased anything you need to simulate any one of these, with just some slight twists in the code. But on the software side, we haven't even come close to doing anything particularly crazy. I mean, you could stick any random arbitrary function in here. You could have random noise, and I mean, this wouldn't feel like anything interesting and wouldn't replicate anything physically, but you could do it. And any function you could possibly dream up, you could apply it to the motor and have a pin that basically physically replicates whatever the hell this function is. That means that not only can we replicate any real physical pin that you can put into a lock, you can make physically impossible pins. You can make pins that somebody couldn't even dream of replicating with a piece of metal. So I think that's pretty cool. This guy can replicate any real pin as well as any non-real pin, as long as you can actually pick it. So far, it wouldn't be particularly fun to simulate a pin that you can't pick that's unpickable, like one of these ones from Stuff Made Here or something like that. So now I'm going to do a version of the game where not only does it swap between different heights of the shear line, but it's also going to randomly pick one of the 3 different variations of the pin type. Here you can see it started with a standard pin. While I'm working away at this, I just want to say that if you like this video, I'd really appreciate if you hit the like button and subscribed. It really helps out with the algorithm and helps get this video out to more people. Now we got a spool pin. Not giving me too much trouble. Also, please leave a comment, not only because it helps with the algorithm, but also, like, especially if you have an idea for a future video, because as much as I think that I have cool ideas for videos, I'm kind of running out, so I would be very thankful for any suggestions you guys have. Alright, well, it looks like I managed to win. Thank you so much for sticking around to the end of the video. I hope you enjoyed. I hope you learned something new. If you did enjoy, I do think you should click right here to watch my fishing rod video, which is kind of like a precursor to this one and features some very similar themes. It's like a prequel to this. But yeah, thank you so much. I really appreciate it, and I hope to see you next time. See ya. Bye-bye.